Yay! Last bit of differentiation. This is the end of Unit 3. So at the end of this, you will theoretically be able to differentiate anything I give you. Unfortunately, good news, bad news, it's parametric differentiation. And I think, I might be wrong, but I think parametrics were one of those things that were covered towards the end of last year when assignments became optional. So some of you are not going to have any idea what's going on because you did not do anything with parametrics. Some of you are not going to have any idea what's going on even though you did things with parametrics. So I don't want you to panic too much because what I need you to know about parametrics is very basic. Like all I need you to know right now about parametrics is that they're broken into two pieces. You have an X component and a Y component. I'm going to put things here, like sine. I don't care. I'm going to put whatever I want, and I'm going to put cosine here. This is a really boring parametric, but we can talk about that later. So this is a parametric relation. So X is a function of t, and Y is a function of t. There's a t, right? It's three-dimensional because you have X's and Y's and t's. That's kind of all I need you to know about parametrics. There's a whole lot more to know, but that's where we're going to start. So as long as you can see an X and a Y and a T, then you're in really good shape. Okay, so here's our goal. Our goal is to go find dy dx. Great, not a problem. Been doing that for weeks now. So this is asking you to take the derivative of y and take it with respect to x. But the problem is, if I come up here to y, here's y, remember I can see it, and I take this derivative the way I think I know how to take derivatives, I would be finding the derivative of y with respect to t, because t is my variable. And then the same issue is true with x. If I came up here to take a derivative of x, I'd be finding the derivative of x with respect to t. And these are not the same letter. Okay, so really basic parametric stuff. Here's what we're going to do. We're just going to cheat it a little bit, and we're going to use all of our algebra rules and make it work for us. So if I go take the derivative of y with respect to t and get dy dt, and then divide that by, sorry, that y looks so weird, dx dt, then algebra tells me that the dt's cancel, and I'm left with dy dx. The end. Is that too fast? Let me show you. Let me show you with a little keep, change, flip action. So what I'm doing is I'm taking dy dt and dividing it by dx dt. Keep, change, flip. So I keep, I change, I flip diddy-doo-dah, and again, the dt's cancel away, and you're left with dy dx. The end. So for this that I'm now making an example, I would take the derivative of y with respect to t. Derivative of cosine is, sorry, I want to write all of this down so that there's no surprises. The derivative of cosine is negative sine t. And then I would take the derivative of x with respect to t. The derivative of sine is cosine. Done. The end. 100 points. Extra credit. Sure, you could clean it up here, because why wouldn't you? But you don't have to. So let me show you what it looks like to work with parametrics a little bit. Like, what if I didn't just say find the derivative? What if I asked you to write the equation of the tangent line at t equals, what have I made here? How about just t equals 0? I don't want to hurt your little brains. So we're writing a tangent line. We're writing a line. And it does not matter what world you're in. So we've done it in rectangular world. We've written tangent lines. We're about to write a tangent line in parametric world. Down the road, a ways away. We're going to do this in polar too. So it doesn't matter what world you're living in, you need a point and you need a slope. So, okay, point, let's start with point. I need an x and I need a y. And lucky for you, those were given in terms of t. So all I have to do is scroll up because I already can't remember. X is sine, y is cosine. So sine of 0 is 0, cosine of 0 is 1. There's my point. My xy coordinates are 0, 1. Now I need a slope. And again, it does not matter what world you are living in. Rectangular, parametric, polar, slope is always a change in y over a change in x. So lucky for us, we already found that to be tangent of t. And then we're going to go evaluate that when t is 0. And don't worry, I know the tangent of 0 is 0. So if I'm dealing with a slope of 0, I'm dealing with just a horizontal line. So this is just going to be y equals 1. The end. Not the end. I mean, we have one more thing to do, but the end for this. All right, last thing. I'm gonna build you up to this. So hold on. If I have a function like something super friendly, and I ask you to go find its second derivative, you wouldn't panic, right? You would just step yourself there. So I could ask for third, fourth, fifth derivative, however I feel that day, but you'd have to start and take one derivative at a time. So you'd pull a power, you'd subtract 1, and then you'd do it again. No big deal. You're just taking another derivative and you'd be finished, and that would be great. Okay, and then let me remind you of implicit differentiation. So let me write something really quickly, like the sine of y plus x squared minus 2y equals 32. And we're going to go differentiate both sides of this with respect to x. Why is it with respect to x? It just depends on the question. So that's about to change, and that's why I'm stalling here. So if I do implicit on this equation, the derivative of sine is cosine, and then you take the derivative of the inside. And so our inside would be dy dx. Plus, pull a power, subtract 1. The derivative of this inside would be dx dx. I know we've never written that before. Really sorry. I just want to show you that it's there and we don't need it because something over itself, this is 1. It's just 1. Minus 2 dy dx's equals 0. Okay, so those are just reminders of other things that we're going to kind of put together so that we can find second derivatives of parametrics. It's not as straightforward as this wonderful second derivative bounce was. So parametric second derivatives. All right, I want to use the same function because I'm not feeling very creative this afternoon. X is sine, y is cosine. But I kind of want to do it, no, that's fine. We'll do it within the question. So we already have a first derivative. So we have a dy dx. It was tangent. Remember? I sure do. We're in the same situation where if we go and take this derivative of tangent t and we do it the way we think we're supposed to, we're going to be differentiating with respect to t. And so that's a problem here. Second derivatives look like this. Notation for a second derivative looks like this. Because this is your operation and you're doing it to y. You're taking the second derivative with respect to x of y. But just like we can do with a first derivative, a d dx of y is dy dx. We can smush it up there too. So what happens when I have this first derivative and then I come over here and I say, okay, let me go take the derivative on both sides with respect to x. Well, the left-hand side does what we need it to do, and you get your second derivative of y with respect to x, and that's great. But check out the right-hand side. This is weird and new. Maybe not weird, but definitely new. We are differentiating tangent of t, but x is our variable. This is implicit differentiation. So we're going to start on the outside. The derivative of the outside would be the derivative of tangent, that's secant squared of t. But then you have to go inside. So I go inside, my input is t. I'd have to multiply this by a dt over dx. And let's talk about what that means. This means please go differentiate t with respect to x. Now this with respect to x business, I'm very comfortable with because that's kind of how we've been doing everything up until 5 minutes ago or whenever this video started. But differentiating t with respect to x is difficult, not impossible for this question, simply because my question doesn't have t as a function of x, it has x as a function of t. So if I were feeling very ambitious, I could go solve this for t and get some function of x in here and go take its derivative, and that would work and that would be okay. But not only am I not ambitious, but I'm also lazy. So instead, watch the algebra. Secant squared is fine. He's going to live here. What's the backwards of keep, change, flip? I'm going to undo the keep, change, flip. I'm going to undo the keep, change, flip. So I'm going to make it back into a division problem. So I didn't undo that part, but turn it back into a division problem and flip it back underneath. Makes it a dx dt. What? That's not any better. Yeah, it is, because you already did this. Like, you already have this. It's just way up here, and it's been forever since we looked at it. But hold up. Here it is. We found dx dt while we were taking the first derivative. It's cosine. If you don't remember, that's fine. You can do it again. Remember that this is x, and we're differentiating with respect to t, and that's what's in there. That's fine. So this answer is a secant squared over cosine. Which, oh my, please don't leave that. You wouldn't actually leave that, would you? It's secant cubed. Or 1 over cosine cubed. Okay. That is second derivatives of parametrics. It's weird, but it's weird because you're uncomfortable with parametrics, and me even saying the word parametric is upsetting, but it's not new. And I don't mean that in an insulting way. It's not new because it's just implicit. There's a chain rule. It's uncomfortable because you've got t's and x's and y's and all kinds of letters that you weren't using before that you're using now. All right, so let's do the thing where I make an example and you pause and try it. So here's an example. I'm making it up so you know it's going to be excellent. Let's not do trig. Would that make you happy? What if I did like a 3t squared minus 5t? And what if I did like a root t? Who cares? I made it up. It's going to be great. So you have two things to do. And you should pause and unpause between them. First, you're going to go find dy dx. And then you're going to go find the second derivative of y with respect to x. All right. Ready, set, pause. And then come back and let's see how your first derivative went. So this is going to be a dy dt over dx dt. I can tell you one of the most common mistakes, because when parametrics are written, they're written in alphabetical order, like you write x and then y. But when you differentiate, it's got to be change in y over change in x. So one of the most common mistakes is just to be upside down. So dy is 1/2 y to the negative 1/2. T to the negative 1/2, my goodness. Over dx dt would be a 6t minus 5. Could I clean it up? Sure. Am I going to clean it up? Yes. I'm actually going to clean this one up because I'm about to use it again, because I have to take its derivative to use it again in the second derivative. And I don't know. I guess I just don't really feel like taking this derivative as is, but you could. It wouldn't be terrible. So I'm going to do my exponent rules and rewrite this down here. I lost my 2. And then I have 6t minus 5. Is that better to differentiate? I don't know. Depends on your mood. I guess I'm going to rewrite it again because I don't feel like doing a quotient rule. I'm going to think of it like this. 6t minus 5, close, and the whole thing is to the negative 1. All right, so let me dive into my, my second derivative. So your second derivative with respect to x is just your first, is is the derivative of your first derivative. So you're going to start the way you think you should. And this has got a chain rule with a product inside. It's going to be so fun. So I'm going to pull the power, keep everything else the same, and subtract 1. And then I'm going to go inside there and start taking more derivatives. Well, inside there is a product rule. And I've got first, derivative of the second is 6. So watch me be lazy. Now it's a 12. Plus second, derivative of the first would be a pull a half, cancels the 2. And then I just have t to the negative half. And then I go inside and I multiply by the derivative of the inside of that, which would be a dt dx. And at some point, I kind of hope you skip this step and go straight to popping it underneath with just a dx dt. At some point, I hope you're there. I lost my x. I'm sorry. That's an x. I understand it might not be right this second. All right, so dx dt, I might have to come back and look, but if you're diligent with showing your work, it should be right here. And you want to make sure you pull it before you've done any cleaning, because sometimes things will cancel away, but they're actually part of the derivative. So maybe you're super lazy and you don't even write this. You just go straight to 6t minus 5. That's it. That's what you got to do. If you chose to do a quotient rule on this, it would clean up maybe a little bit nicer, but I don't care. I don't care. I don't care. It's more important that you know how and not worry about cleaning right this second. All right. Let me know if you need anything.